Welcome to this lecture on parasitology. Today, we are going to explore a fascinating and dangerous microscopic invader known as Plasmodium vivax. Imagine playing a high-stakes game of hide-and-seek inside your own body, where the hider can go to sleep for months before launching a massive attack. This parasite is a master of disguise and survival, responsible for a specific recurring type of human malaria. By the end of this session, you will understand not only its complex biology, but also the mathematics we use to track its explosive growth. Let us begin by understanding exactly what we are dealing with. Plasmodium vivax is a microscopic, single-celled protozoan parasite. It is one of the primary pathogens responsible for causing human malaria across the globe. But it does not travel alone. It relies entirely on a biological vector to reach us. Specifically, it is transmitted exclusively through the bite of an infected female Anopheles mosquito. When this mosquito takes a blood meal, it unknowingly injects the parasite into the human bloodstream, kicking off a highly coordinated invasion that we will explore next. Now that we know what this parasite is, we must ask why it is so important to study. Understanding Plasmodium vivax is absolutely critical for global public health. It is the most widespread malaria parasite in the world, particularly in regions outside of Africa, such as Asia, Latin America, and the Middle East. Millions of people suffer from the debilitating, shivering fevers and severe anemia it causes. Beyond the physical toll, this specific infection creates massive economic hardship in affected communities. This widespread suffering makes mastering its biology a global priority. To understand how it causes such widespread harm, we need to look at its journey inside the human host. Once the parasite enters the body, it does not just float around randomly. It undergoes a highly structured, complex life cycle divided into two main phases. First, it travels straight to the liver for the exoerythrocytic cycle, where it quietly multiplies behind closed doors. After this liver phase, an army of parasites bursts out into the bloodstream, initiating the erythrocytic cycle. It is this blood phase that hijacks red blood cells and triggers the intense fevers. This brings us to the most unique and dangerous feature of this specific parasite. Unlike other malaria parasites, Plasmodium vivax has the terrifying ability to form dormant liver stages known as hypnozoites. Think of these as ticking time bombs. These dormant forms can remain completely inactive for extended periods, sometimes months or even years, before suddenly reactivating. This reactivation leads to clinical relapses of malaria long after the initial mosquito bite. If doctors only treat the active blood infection, the patient will continuously suffer from mysterious relapses. This is why targeted drugs like Primaquine are essential to hunt down these hidden liver stages. With the biological foundation laid, let us shift to how medical professionals handle an active infection. To truly understand the severity of a Plasmodium vivax infection, doctors and parasitologists must measure exactly how much of the patient's blood has been hijacked. We do this using a crucial metric called parasitemia. Parasitemia represents the percentage of red blood cells that are actively infected by the parasite. This measurement is vital because it helps clinicians decide how aggressive the treatment needs to be, and it allows them to monitor whether the prescribed antimalarial drugs are actually working to clear the infection. To calculate this metric, we use a straightforward mathematical ratio. The formula compares the infected cells to the total cell population. Here, P represents the parasitemia, expressed as a percentage. The variable I stands for the number of infected red blood cells, counted under a microscope in a specific blood sample. The variable T represents the total number of red blood cells, both healthy and infected, counted in that exact same sample. Conceptually, we are just finding the fraction of invaded cells and converting it to a percentage. If the value of I increases while T remains constant, the parasitemia P will rise, indicating the infection is worsening. Let us see this formula in action with a concrete example. Imagine a patient arrives at a clinic with severe chills. A technician examines a blood smear and counts a total of 5,000 red blood cells. Out of these, 125 cells contain the parasite. We are asked to find the parasitemia percentage. First, we substitute our known values. I equals 125 and T equals 5,000 directly into our equation. Dividing these gives a decimal fraction of 0.025. We then multiply by 100 to convert this raw fraction into a standard percentage. The final answer is 2.5%. In a clinical setting, this high level of cellular destruction requires immediate medical treatment. Now that we know how to measure the current infection, we must understand how the parasite spreads so quickly. Another crucial mathematical concept in parasitology is understanding how rapidly the parasite population explodes inside the human bloodstream. During the erythrocytic cycle, a single infected red blood cell bursts and releases multiple new parasites, called merozoites. These merozoites then immediately infect new, healthy cells. This creates an explosive, exponential growth cycle. This rapid multiplication perfectly explains why a patient can go from feeling completely fine to being critically ill with massive fever spikes in just a matter of days. To predict this terrifying spread, we use an exponential growth model. In this formula, N represents the total number of parasites present in the blood after a given amount of time. The symbol N0 is the initial number of parasites that successfully entered the bloodstream from the liver. The variable M represents the multiplication factor, which is the average number of new merozoites released when a single cell bursts. For Plasmodium vivax, this is typically 16. Finally, the exponent C represents the number of complete reproductive cycles, with each cycle taking exactly 48 hours. As the number of cycles C increases, the total population N grows exponentially. Let us apply this model to a terrifying real-world scenario. Suppose a patient's liver releases exactly 100 merozoites into the blood. We want to calculate the total parasite load after 6 days, or 144 hours, if left untreated. First, we find the number of cycles by dividing the total time of 144 hours by the cycle duration of 48 hours, giving us exactly 3 cycles. Next, we plug our initial population of 100, our multiplication factor of 16, and our 3 cycles into the formula. 16 to the power of 3 is 4,096. Multiplying this by our initial 100 parasites gives a staggering final answer of 409,600 parasites. This massive, synchronized destruction triggers life-threatening anemia. Now that we have explored the biology and the mathematics, let us bring it all together visually. Here you are looking at the complete life cycle of Plasmodium vivax. Notice how the diagram is split between the mosquito stages at the top and the human stages at the bottom. Follow the arrows from the mosquito injecting sporozoites down into the human liver. There, you can clearly see the exoerythrocytic cycle and the dangerous dormant hypnozoite hiding within the liver tissue. From the liver, the arrows guide us into the circular erythrocytic cycle in the blood, where the parasite matures from a ring stage into a bursting schizont, releasing merozoites. Finally, some of these develop into gametocytes, ready to be taken up by another mosquito, completing this vicious cycle. We have covered a tremendous amount of ground today, so let us review the most important ideas. First, Plasmodium vivax is a highly successful and resilient parasite responsible for a massive global burden of recurring malaria. Second, its defining characteristic is the ability to hide in the human liver as dormant hypnozoites, which act like ticking time bombs, causing disease relapses. Third, we learned that medical professionals use parasitemia to measure the exact percentage of hijacked red blood cells to diagnose infection severity. Finally, we used exponential growth models to track the terrifying, explosive multiplication of the parasite in the bloodstream. Mastering these biological and mathematical concepts is your first crucial step toward fighting this disease.